Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to calculate what's called the escape speed of a planet. So first of all, I want to talk a little bit about what escape speed means or what it is. And probably most of you or anybody watching this video has probably heard the expression that what goes up must come down. And inherently what that means is that if you throw something in the air, if a human throws a rock or a golf ball or something into the air, they typically will come back down unless it lands on a building or maybe gets caught by an eagle or something. But even in the absence of being caught by an eagle, it's not necessarily true that just because you throw something up, it must come back down. It is in fact possible to launch something from the surface of a planet at a high enough speed that that something can escape the gravitational influence of the planet. And the speed at which you have to launch the particle at is called escape speed. So what I'm going to do in this example is we're going to calculate the escape speed for a particle launched from the surface of the Earth. Or maybe I should say a planet with the same mass of the Earth and the same radius of the Earth, but no atmosphere. And the reason I throw that no atmosphere in is because escape speeds tend to be very large numbers. These tend to be measured in maybe even kilometers per second. And if you launch a particle through the atmosphere of the Earth at several thousand meters per second, it'll pretty much just vaporize like asteroids or like rocks do when they hit our atmosphere coming from space. So ignoring atmospheric effects, we're going to calculate the escape speed of an object launched from right about here, from where I'm at here in Michigan. So we're going to be ignoring, again, some really big effects, one being air drag. Second, we're also going to ignore the rotation of the Earth because that's actually a significant factor. And we're just going to worry about the speed that the particle is launched relative to the planet. So I'm going to draw a picture of my particle, whatever it is. I'm going to call this position 1. And imagine it's launched in this direction. It's got some sort of velocity that I would call something like v1. And this particle, as it moves away from the Earth, it'd be going slower and slower and slower. But the idea is that position 2, this particle's out here somewhere, it's still moving. It's got a speed that we might call something like v2. And it leaves the gravitational influence of the planet. Now, when you're looking at problems in mechanics like this, there's two main ways that we can analyze this object. One would be by Newton's second law. As this object is moving away from the Earth, the only force acting on it is the gravitational force, which by Newton's law of gravity looks something like this. The gravitational force is proportional to the two masses, falls off with distance squared. However, because the radius is changing, the acceleration is not constant. And this becomes a reasonably tough math problem. Not super tough, but it's it requires some methods of calculus and differential equation theory to apply this type of approach for this problem. Another method we can hit this with is work energy. And it turns out work energy is a really nice, easy way to attack this problem. So what we're going to do is we're going to call this position 1, this position 2, and I'm going to write out the work energy theorem. Right, PE1 plus KE1 plus work equals PE2 plus KE2. Now, let's talk about the kinetic energies. So the KE1 term is going to be 1/2 m v1 squared. The KE2 term is going to be for the kinetic energy at position 2. Now, position 2, it's gone. And what speed it leaves at, for now, I'm just going to put a v2 there and talk about it later. So for now, I'm just going to put 1/2 m v2 squared under the KE2 term. Right. Now let's chat about the potential energy terms. So when you first learn about potential energy in physics, usually you start with gravitational potential energy equal to mgh. And this is true as long as the g doesn't vary, as long as you're talking about at the surface of the Earth where the gravitational field strength is around 9.8 Newton per kilogram. This is not true in a cosmic sense. This is not true if the particle gets far enough from the Earth that the gravitational acceleration significantly changes. In those cases, we want to use the more general gravitational potential energy term, which looks like this. minus big G, big M, little m over r. Now, the big M, little m, if you look this up in a book, you might see mass A and mass B, or mass 1 and mass 2. It doesn't really matter as long as you note there are two different masses. In this case, we've got the particle, and then the Earth will be the second mass. I like to use a large M and a little m because it's quite common in these problems to have a large planetary object like the Earth and a small object like my golf ball or rock or whatever we're pretending to shoot from the Earth. So our PE1 term, we can write minus big G, big M, little m over r. And that radius is going to be from the center of the rock to the center of the Earth. So that's what we would call the radius of the Earth. The PE2 term. So this object here at position 2, the r would be from the object to the center of the Earth. And the idea here is that position 2, this thing's gone. R is getting bigger and bigger and bigger, or mathematically we say R is going to infinity. When R goes to infinity, this potential energy term goes to 0. Or we say that the datum is at R equals infinity. So the PE2 term is 0. And again, very important to realize why, because the potential energy is minus G, big M, little m over R. But for position 2, the R, which is this distance to this object, is basically infinitely large. It's getting bigger and bigger and bigger, and then that fraction goes to 0. Okay, work term. Anytime you write out the work-energy theorem, you need to evaluate the work term. And the way you do that is you look at a free body. If I look at a free body of this rock while it's right here, the only force on it is the gravitational force. Or I should say the only relevant force. The gravitational force between the Earth and that rock, right, which can be calculated by Newton's law of gravity. However, when we use these potential energy terms, we are taking that into account. So that's what the potential energy terms do for us. So the gravitational force is taken into account, and there's no other forces present. So the work done on this system, we're going to say is 0. So here's what the work-energy theorem has to say about this rock launched from Battle Creek, Michigan here. It's got a kinetic energy equal to 1/2 mv squared. It's got a potential energy equal to this term, where this radius is the radius of the Earth. Then position 2, it's out in outer space, it's gone. It presumably will have some sort of kinetic energy, as it probably will remain moving. But its potential energy would be 0 because of the infinite radius on the potential energy term. All right. This equation is good, I would say, in kind of a general sense. I'm going to talk a little bit now about this term escape speed. Escape speed means the minimum possible speed you can launch the particle with and have it leave the influence of this planet. So the minimum value for V1 will correspond to when this particle just barely gets away. If it just barely gets away, it's not going very fast. So what I'm going to do here is I'm going to force this term to 0 as well. This V1 now will be the escape speed. I'm going to rewrite that equation. And I'd like to take a moment here and just algebraically solve this for V1. One thing to note is that we've got a little mass here, and a 0. So this mass, this little guy here, can be divided out. This term can be added to the right. And if we solve that for V1, we're going to get this expression. And times 2. So, and again, I got this just by adding this term to the right, multiplying by 2, square rooting it. Now, I'm going to, in a couple minutes here, I'm going to pause the video here, put numerical values, and get a numerical value out. But before I do that, I'd like to chat a little bit about what this equation is saying. You'll notice that the V1 here is a function of the mass. And you'll notice the mass is in the numerator. And what that means is larger mass, higher escape speed. And hopefully that would make sense. Larger mass means we'll have a stronger gravitational field, stronger gravitational forces pretty well everywhere, and it's tougher to escape the planet. I'd like to also point out here, though, that Also, it depends on the radius, but you'll notice that the radius is in the bottom of this fraction. So the larger the radius, the smaller the escape speed. Or working that the other way, the smaller the radius, the larger the escape speed. Now, the Earth is not going to change in mass, or I'm sorry, by radius in any significant way here, unless we have some majorly catastrophic event like we get ran into by another planet or something. But other than that, the Earth's radius is going to remain pretty well constant for the next foreseeable future. However, astronomical bodies like stars have an extremely large mass. The mass of our sun is around 2 times 10 to the 30th kilograms. And stars can kind of collapse on their own gravity, under the influence of their own gravity as they run out of fuel. So when a star starts collapsing, its radius gets smaller and smaller and smaller. Then the escape speed gets bigger and bigger and bigger. And once the star is at a radius that the escape speed is equal to 300,000, 3 times 10 to the 8th meter per second, which is the speed of light, you now have what's called a black hole. So anyway, I'm going to pause this for a moment while I work out some numerical values. Okay, so I'm back, and the numerical calculation just takes a couple minutes, but right here, this is the gravitational constant, 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared. This would be the mass of the Earth in this example, 6 times 10 to the 24th kilograms. The radius of the Earth, 6.4 times 10 to the 6 meters, times 2. Out will come about 11,000 meter per second. And 11,000 meter per second is pretty fast. Just to kind of put this in comparison, a 30-06 will fire a bullet at about 1,000 meter per second. Would be a pretty fast round. So this is about 11 times the speed of a 30-06. If you actually fired a particle at 11,000 meter per second, it would probably just vaporize upon impact with the atmosphere of the Earth. Very few things actually can handle this type of speeds. Rocks, as they fly through space, are moving at speeds that are measured in kilometer per second. And you can watch them hit the atmosphere on any given night. If it's a nice, any given clear night, if you go out and look up, and you'll see those, what we call shooting stars, and those are rocks basically disintegrating on impact with our atmosphere. So anyway, the point of this video is to describe what escape speed is and how it's calculated using principles of work and energy. I hope that this has successfully done that for you. Have a great day.